Thanks for coming today. I'm actually going to talk to you about some work that I did at Notre Dame, not at UBC, but when I was at Notre Dame working with Sidney DeMello. So I think we can all agree it would be nice if we knew what students were thinking, or at the very least, if we had some idea of how hard they were thinking. So for example, if the student was thinking, oh my gosh, this learning material is so easy, versus if they are thinking really hard and they still don't get it. So they've been on this topic for a long time and they are still not really getting the concept. So some previous work has tried to get at what students are thinking or feeling during learning with things like eye gaze, mouse movements, keystrokes, and speech. But what we're going to do today is talk about some work trying to move towards going sort of right to the source and looking at what the brain is actually telling us. So we're going to do this by using EEG, which is essentially electrical activity generated from the neuronal activity in your brain that's passing through the scalp. So one of the benefits to using EEG, at least in terms of looking at brain activity, is that at the state of the art right now, it's sort of the least invasive and the most cost-effective way to actually look at brain activity, because right now we can't really put students in the scanner and ask them to learn. That would be quite expensive. So sort of as an overview of what different frequencies we'll be looking at today, or what frequencies are used to build the models today, are things like theta, which is associated with things like memory encoding and retrieval, alpha, which is sort of usually consistent with the relaxed, wakeful state, beta, which has been associated with sort of executing movements or motor areas, and then gamma, which has been previously associated with like sensory processing. So one of the reasons that we're sort of able to do this research now is because of the improvements in EEG over the years. So EEG used to have to be recorded using a pen, and the sensors could be very intrusive, so something like this. So imagine wearing this type of cap and trying to learn. It might be sort of interfering with actually the task at hand. So fast forward to today, we have sensors that look more like this, where you can just have a cap that sort of sits on your head. Importantly, dry electrodes, so you don't need to use a saline and attach them to the scalp. So this sort of setup is much more conducive to like a learning task. And just to sort of give you guys some examples of what we've been able to do with EEG recently is actually use things like brain-computer interfaces, where the people can actually take what's happening in the brain and interact with the environment outside. So for example, this woman is using her thoughts to actually dictate this robot arm to drink out of this straw. So some model has been trained on the signals in her brain, and she's navigating this arm just by thinking. Whereas this guy is actually playing the game Pong, which I don't know if you guys are familiar with that, with his thoughts. So we're not quite there with learning in terms of having this sort of like full-on feedback system, but there has been a lot of research showing that you can detect cognitive load very accurately using EEG. In terms of overview of cognitive load theory, sort of the idea is that working memory capacity is limited, and cognitive load is how much space in working memory is being used. So in relation to learning, there's some research that suggests that as you build up cognitive load to a certain degree, if the cognitive load is actually contributing to your schema formation or sort of helping you build that model of that topic, then it can better performance. So higher cognitive load can actually help performance. But if your cognitive load gets too high and sort of overflows your memory resources, then learning can be stifled. So what we need to kind of do is find some optimal level of cognitive load for each person to sort of try to boost their learning. One of the things that is particularly important for that then is difficulty, because how difficult the material will play a role in how much load you're experiencing. So some previous studies that are particularly related to this are a study that used EEG to measure cognitive load, and they found that their predicted levels of load positively related to the difficulty of the tasks. So they had tasks that varied in terms of difficulty. And they also found that load negatively related to performance, and in particular that was for basic tasks like a digit span or a logic task, but they found no relationship with complex tasks. So there's still sort of some open questions there about how load would relate to like sort of real learning, where you're trying to develop a model of some concept, for example. Another study has shown that it's actually, you can use EEG, or predicted load, to tell if the task is easy or difficult. So in this study, they had children and adults read easy and difficult passages in an intelligent tutoring system setting. And they had one electrode EEG, so just one single electrode in the head, and they were able to use machine learning classifiers to predict whether the passages they were reading were either easy or difficult. So sort of that being said, EEG can be used to assess cognitive processing. There's quite a bit of work on that, and we see that it changes with the level of difficulty of the task. So then moving sort of forward to our overarching goal is we want to collect EEG while students are in this ecological learning environment and build a detector of cognitive load. And then eventually the goal would be to try to build a system that has some real-time optimization and feedback based on the student's cognitive load. So for example, if the load is too easy, then we might want to increase the difficulty. If their load is exceeding their memory resources, might want to back down the task difficulty. Or if it's sort of at an optimal level, we might want to maintain that level of difficulty for the time being. This project, however, is focused on this first step. We want to see if we can actually build a detector of cognitive load in an intelligent tutoring system. So for the current study that we completed, we had high school students wear an EEG cap, similar to one of the ones I showed you before. And this was done in collaboration with Quasar USA. They're the ones who actually developed the cap. And then we're going to actually try to manipulate the levels of difficulty in two phases of an intelligent tutoring system. So we're going to manipulate it ourselves. And then we want to see when students are interacting with the intelligent tutoring system and they have an EEG cap on for an hour and a half, how valid is the EEG data in general? Do we lose it over time? How does that work? And then two, is the detector actually sensitive to our manipulated levels of difficulty? So the tutor we used is called Guru. It is a dialogue-based ITS where this animated tutor basically engages a student in a collaborative conversation that references this multimedia workspace. So the students here interacted with two topics. The first topic they interacted with, or they were counterbalance order, but one of the ones was on maintaining temperature, so how your body sort of maintains this core temperature and homeostasis. And then the second one was on trophic levels, like how does energy move through a food chain. So we manipulated difficulty, like I said, in two different parts of this ITS, which I'll kind of go into more detail about now. The first one was in the what's called common ground building instruction phase, which is sort of like a collaborative lecture. So here, basic terminology is covered. So the tutor is basically laying the groundwork here, the maybe tough vocabulary words they haven't heard before. So to manipulate difficulty here, what we did was focus on manipulating the language. So for example, they would, see, this is a difficult version. So here, it's once the brain detects increased heat, it instigates pumping of the blood near to the skin. So the same content, but said in an easy way, is the brain will realize that it is too hot. Then it will begin to pump blood close to the skin. So you can see, just in this one example, that the difficult version has a longer sentence, different vocabulary, whereas the easy version is sort of more syntactically easy sentences. Oh, sorry, I didn't realize there was something there. So what we did was compare the, to sort of test that manipulation, we compared the easy and difficult versions using cometrics. We used the easeability component scores. And what we found was when we compared narrativity, syntactic ease, and referential cohesion, for all three of these measures, the easy versions were significantly higher, meaning easier. We also looked at their Flesch-Kincaid grade levels, which were significantly different. The easy versions were around a grade level of 5, and the difficulty versions were around a grade level of 9. So these students were in high school, so the grade level of 5 would be much below their average reading level. The second section of the tutor that we manipulated was the scaffolding section. So here, whereas we manipulated language in the instruction section, here we manipulated how the questions were asked or what type of answers a student needed to give. So here the tutor is going to ask the student a question, process the student's answer, and provide some feedback or explanation of the topic. For the difficult questions, they're having to answer questions like fully in construction, so it's open-ended questions with no hints, no prompts. Whereas the easy questions are just true-false questions, so they get to make a decision whether it's true or false. In terms of how it worked, for each topic, they would go through the instruction phase and the scaffolding phase, and the difficulty would be manipulated at the midpoint. So for topic 1, for example, the first half of the instruction would be with the easy language, And then the difficult language for the scaffolding, they would answer the true-false questions and then the open-ended questions. For topic 2, then, the order of the difficulty would just be switched. Importantly here, because we're manipulating difficulty, we also wanted to ask them about their subjective reports of difficulty, sort of get a manipulation check. And so at the midpoint and at the end, we also asked them to rate their difficulty, or the tutor would ask them to rate their difficulty. The EEG headset that we used was one that looks like this, and this is the experimental setup. It was a 24 dry channel electrode system that was again developed by Quasar USA. And they developed this headset with sort of in mind that it would be able to be used for more ecological data collection. The next thing that I'll talk about is, so we collect the EEG data, but one thing we need to keep in mind is that we need to know what's high cognitive load and what's low cognitive load. So we need to train the detector on some tasks that we know would induce low or high cognitive load. So we did that by having the students go through a variety of tasks beforehand. These tasks, these 4 are common tasks people use when they're looking at cognitive load. So what we did was have them go through an easy and difficult version of this, or low cognitive load, high cognitive load version. So for example, for column addition, they would go through a part where they would just be adding numbers with 1 digit versus numbers with 3 digits. We also had them go through like an eyes closed and eyes open training task. So the eyes open would be, they would just be looking at a fixation cross and for like 15 seconds. So these 2 tasks would be like the epitome of no cognitive load because there's no task at hand. We also used some guru-related training tasks. So like if you remember, the difficulty manipulation had easy and difficult language. So here we had a guru training task that actually sort of had a preview of the lecture on a totally different topic that had easy and difficult language. So we could use this to train the detector. We had 12 high school students in total. It was within subject design, so they completed both topics. And the sort of general setup was they would come into a lab, they were tested individually, get set up with the EEG, go through the training task, the guru training tasks, and then go through both topics, and then finally the eyes training tasks, so the eyes open and eyes closed tasks were done at the very end. Okay, so now I'm going to explain. We built 4 different models. Like I said, I've just went over all the training tasks we did, but there's some question of like, how many training tasks do you need and what types of training data would be the best for this? So for example, this is one of the first studies that's trying to look at training a cognitive load detector in a learning environment. So do you need information about the learning environment to train the detector, or can it be totally domain independent? So the first one is an eyes open versus all other training tasks. So here in the easy column, that's what was trained as the low cognitive load state, and here is the difficult as the high cognitive load state. So in the first one, it was just eyes open, which is like no cognitive load versus every other task that we had. The second one was also an eyes open low state, but the high state was just the guru training tasks. Then we had 2 models that actually utilized the easy and difficult training tasks that we had. So here, notice that the easy versions of the training tasks are in the easy column, whereas the difficult are here. And then the only change in the last model is that we actually separated the guru train. So this one included all the typical cognitive load tasks plus the guru easy, and same thing for the difficult. Okay, so an overview of sort of the classification and output that I'm going to go over is for the whole session, we take the 2-second epochs of data and classify those as high or low cognitive load. So the model was built, if you want more details, it's in this paper by McDonald and Soussou called Q-state. So basically, the data is trained using partial least squares regression, and they use a k-fold stratified cross-validation method, which basically splits the data into 6 different sets, and the stratified part meaning that for each of the sets, the mean is equal to trying to keep the distribution of the data the same across the different folds. Okay, and then sort of important to note here is that when I go over this, the output is normalized to values that range from 0 to 1. So the graphs I'll show you, 0 meaning the lowest, or 1 meaning the highest. Okay, so the first question that I'll go over is, like I mentioned, there could be a lot of things that could go wrong here. We have students, the headsets were originally made for adults, so there's some potential head circumference issues, the overall time that they had the data set on, or the EEG headset on, and also just the fact that they were able to move around quite freely in their chairs. So what we did was look at how much of the data was usable. So for the 4 models, did the data provide any output? Because in some cases, if the sensors became detached, there would be no output. So here we have pretty encouraging results in the sense that for the 4 models, there was usable data for about 75 to 91% of the sessions. The next step was to look at the subjective reports, because we want to know first, did they sense the differences in difficulty in our difficulty manipulations? So for the instruction phase, which is where the language manipulated, they reported no significant differences. So the students themselves were not able to pick up on the differences in the language. However, for the scaffolding phase, which is where they had to answer open-ended questions versus true-false, they actually rated the open-ended questions as being much more difficult. So this is what the model output would look like across an entire topic. So you can see here it's 0 to 1. And this is how the cognitive load is sort of fluctuating throughout the topic. So I know this is a little bit hard to see, but essentially this here is the instruction difficult part. Okay, so what I'm going to do for these analyses is take the average of the difficult section and compare it to the instruction easy section. And then I'll do the same thing for the scaffolding. In terms of the instruction phase then, what we found were that out of the 4 models, only one of them, we found a significant difference in the average model output, average cognitive load output. So in some ways this is encouraging because the students themselves couldn't detect a difference. So the fact that our model was able to pick up on a little different, one of the models was able to pick up on a difference is kind of encouraging. For the scaffolding, we found sort of the opposite pattern where 3 out of 4 of the models were actually detected a significant difference in that detector's load. So this isn't sort of in line with the idea that the participants also reported differences in difficulty, so and the models did as well. So yeah, just as an overall picture here, you can see that for the language manipulation, the detector did much worse than for the open-ended versus true-false. There was also the question then of how the participants actually did on the scaffolding. So for the open-ended questions versus the true-false questions. And here we found that participants actually did much better on the true-false versus open-ended. And sort of the final piece of this then is that were the models actually able to predict how students did on the scaffolding questions. And only one of the models was able to, had a significant relationship with that, and that was the eyes open versus every other training task model. So that was the one that basically the low load state basically is do nothing. And importantly here, which is one of the questions that I mentioned at first, is that this is a negative relationship. So the higher the cognitive load, the worse they did. So this is something to keep in mind for future work when we want to try to find that optimal state. We don't want to get to that level, at least with this model's output. So as a summary of what I have just been going over, we had 1.5 hours of EEG data from high school students, and they were using a cap that allowed them to move freely, and also that was originally made for adults. So we think that the fact that 83% validity across the 4 models is pretty encouraging. And then this is one of the first studies to try to, in a real learning environment, try to build a detector of cognitive load and test it. So using our difficulty manipulation, where we would have expected maybe more cognitive load, predicted cognitive load in the instruction phase. For the subjective reports, we found no difference. And for the model output, we found that only one of the models was able to pick up on a difference there. And what's important about this is that the training task might matter, because the one model that did well here was the one that actually included the guru training phases. So for future work, we might want to consider that we do need some domain information when we're doing our training. For the scaffolding phase, again, we would also maybe expect the difficult to be higher than the easy. And for the subjective reports, we did find that pattern. And for the model output, 3 out of 4 was able to detect that difference. And then we were also had some evidence that we could predict performance on the scaffolding with one of the models. So some of the things we'd like to do in the future is potentially get more students. This only had 12 people, so we potentially want to have more to get a bigger sample size. Maybe a more ecological, so oftentimes students will work in groups, so we might want to have more than one student at a time. And then finally, actually look at more levels of difficulty. So as this first pass, we just did one easy, one difficult, and sort of based on what I've been saying before, that might not be the case. We might need to find this optimal level, so different levels of difficulty might help us get there. So for example, if it's too easy, they might not do well, too difficult, but there might be some sweet spot in the middle. So eventually, we would like to get to this point, and that might mean, for example, when the model reaches too high, we back them back down, and we might be able to use data sort of along these lines to get there. So thanks for coming. I'd be happy to take any questions.
We have around 10 minutes for questions.
So basically, the 2011 paper I referred to goes into a little more detail, but essentially it's using those 4 bands, no deltas included, and then it does some like combinations of those models, so some like transformations and including them as well. So. Right.
Can you fine-tune that to sort of try and find their individual versus something like that? Just wondering.
Right. Yeah, so I didn't mention, but each model is actually tailored for each student specifically, so it's not built on the entire data set, it's like each person. So, and that's why the training tasks are so important, because that gives us an idea of how to gauge it for each person. But it might be, like, sort of going back and teasing apart the data a little bit more, we might be able to sort of understand more about the frequencies and what they're telling us. But you know, from this, that wasn't really the goal. It was more about the prediction. Mm-hmm. So the training was done with the partial least squares regression, and then the output is essentially, like I said, I think it basically uses like a multivariate normal probability distribution to give like a real-time estimate of it after the training was done with the partial least squares regression. Yeah.
I tried to see or connect 2 dots actually to yours and the keynote speech this morning, and I think it would be really interesting to sort of know what's the sort of tipping point, you know, when actually cognitive load
Right.
becomes overloaded, right? And especially when you look at the trace sort of data, it
Mhm.
shows actually how students cognitive, right? So so the student might perceive, or there is a cognitive load and there's that sort of, you know, peak. And anyway, so my question is, the conditions are manipulated, right? The
Right.
task difficulty were manipulated, but I think it will be really interesting to consider intrapersonal covariates, so that usually student perceptions of difficulty actually interacts with their overall ability in that target domain,
Right.
as well as self-regulation. So when actually when students perceive tasks to be too difficult, then there's the affect that kind of interferes with their cognition, right?
Right.
So if the students have, you know, high SRL, so that they can actually regulate their emotions, so that they can kind of refocus on those cognitive tasks.
Mm-hmm.
So then I was thinking maybe there's a sort of peak in the cognitive overload, or maybe it's overloaded, but somehow the learner may actually, okay, now calm down, I'm gonna focus on this, and then maybe drop, and then they can't figure it out, and they're kind of going back,
Right.
So my question is, you manipulated conditions, but I was wondering whether you need to consider learner variables in
Yeah.
terms of SRL, affects, and things like that.
Yeah, I
And
think
then
that's
overlay these two, I think might actually give us a really interesting.
Right, yeah, that's a good idea, and it's very appropriate for this session, multimodal learning. But I think that, and people have done some work on like giving the people real-time feedback of their like signal. I think there's a paper that just came out recently that did that gave people like an attention gauge and helped them sort of modulate that. But I think having 2 channels and like affect would be a good good thing to include here.
I think the study is very interesting. Thank you for the presentation. And I find it particularly interesting because we are doing a similar research. And one of the challenges we have experienced is like, okay, when you don't have any signals, it's okay, you know, we can just filter them out.
Mm-hmm.
But for the signals, to check their validity, it's very hard because there is a lot of motion artifact as
Right.
well. Like even blinking makes the data, you know, noisy.
Yeah.
So I'm wondering what kind of methods you implemented to filter out those data.
Yeah.
Or did you ever consider?
So basically the models are built in a way that takes basically constantly update, like retrains the model like in real time, so that if we do have holes in the data, like in the sense that the model does not predict at some times, and if we had that, we don't use that. So that's why I did the averages over the section, because there are points where the model can't make predictions. And so for that's sort of why in this I'm taking the average of this, so there might be a point where we don't have predictions, and in that case I'm not making a prediction, I'm taking the average of that.
Yeah, but still, you know, you might have a motion artifact,
Right.
Like even blinking. The model can give you some data,
Right.
but it's noisy.
Right.
So that's something that we are currently experiencing and trying to solve. So I'm just wondering.
Yeah, the models were originally developed by the folks at Quasar, who we collaborated with on this. So their paper has a lot more detail on how the model is continuously updated, and they specifically try to address things like motion and eye blinks and stuff. But they have some more details in that 2011 paper. Their model is called Q states, and so yeah.
So they use algorithms to filter out the noise so you can get the signals that you're looking at.
Right.
And is that proprietary or will they show you?
You could contact them. I think it's proprietary, but you could contact them. Yeah.
I'm curious what the process is that you went through to choose the 20-node headset. Was that just what Quasar had available, or?
They're working on like trying to develop an electrode system that has less, but the 24 is what they have that like in the basic cognitive load task can get like over 90+% accuracy with predicting high versus low cognitive load. Yeah.
Okay, I just know that there are some companies like Emotive or
Right.
ones with like these 4 to 8 to 12.
Right. I think Quasar is working on a 7 one, so I think that like the overall push is to get lower and lower and to have the dry sensor just basically sit with minimal weight and
Right.
yeah.
I'm interested in applications. You said that, I think you said that there were instances where the predicted difficulty, but students did not report that.
Right. So for the the part where language is manipulated, one of the models detected some differences in cognitive load, but the students themselves did not report any. So in this case, it might be a situation like sort of related to your question, where they aren't perceiving the amount of difficulty that it is to process like a longer sentence or something like that, but they're not perceiving that they're not understanding the sentence.
Restricted to the language.
Right. Yeah, specific to the language piece.
Okay.
Because they actually did report differences in the question piece.
Yes. Okay.
There's a fair amount of research on pupil dilation and cognitive load.
Mm-hmm.
And given it's multimodal, I'm curious if there's also machine learning practice and my practice to be able to track that and get the cognitive load. Have you tried to combine pupil dilation prediction as part of your EEG work?
No, we haven't done any combination of the two. In Sidney's lab, there's quite a bit of work on like eye gaze and detecting like different attention states, like mind wandering or off-task thought, but not in combination with EEG.
What about the kind of user experience for the students? It's quite tiring to wear these headsets.
Right.
Even though it's non-invasive, it's still, you're pretty tired after a short session. How did you factor that into
We didn't find any differences across from early session versus late session to answer that question, but when the study was run, there was extra precaution taken to try to, the students were explained a lot about the EEG and enjoyed, or basically tried to give them the best experience in terms of the participating in research and explaining EEG to them. Yeah.
Sometimes it feels like it's a factor.
Right.
You know, even though it's not invasive, you're fairly exhausted after.
Right.
A session.
Yeah, and also I think it's a part of the, maturation of the form factor as well. Like at the moment we have those form factors, but hopefully, with this research.
Right.
Last question?
We'll take the experience.
No, we close that. Thank you very much.